So, okay, yeah, we're going to do the n queens thing, but we'll get back to here. So here is, all right, I've got PyCharm open. You don't have to use PyCharm. I know a lot of people were using VS Code. By all means, use VS Code. Just don't ask me anything about it because I don't know. Just ask him because apparently he knows stuff about it. I don't know anything about VS Code. I barely know anything about PyCharm, but I know a little bit more about it than VS Code. So this is just the IDE I'm using. So let me just show you how I would expect you to go about doing your lecture. So first of all, you're going to have your GitHub. If you like GitHub Desktop, use GitHub Desktop. If you like to use GitHub with the command line, by all means, use that. That's usually what I would do, but a lot of people are freaked out by that. So I'm just going to pull. Whenever you do anything, make sure you pull. You fetch and pull from origin because any updates will, get updated. You might need to go to your fork of the repo. Let me show you what I mean. If I go here to, if you haven't updated your fork in a while, depending on how you have everything set up, you might have to, let's see here. So we've got several forks. Can I see the forks? Fork. No. All right, never mind. If you go to your fork up here, up around here, there might be a button for like sync with origin or something like that. You might want to do that. So there you go. You're a little bit behind, but you can get updated like that. So yeah, what did it actually say? Sync fork, or what does it say? All right. All right. You hit, exactly. Click the button. We like to hit buttons. It did the trick. We're happy. Perfect. All right, yeah, fetch, okay, and pull origin. Okay, so I'm pulling. I'm 6 commits behind even, right? So give it a second. I think we have all observed yesterday the internet's been a little sluggish lately. All right, cool. I'm all up to date, I think. Well, it's still thinking. Okay, cool. Perfect. So let's say you're thinking, okay, I want to make my lecture. So here's what you're going to do. From main, you're going to say, create a new branch. And you're going to call it, I don't know, let's say I'm doing novelty search, right? So maybe I'll call it novelty search, okay? You create the branch. Oof. I do not know why it's taking so long. Jesus Christ. All right, there. And make sure we are on the branch we actually want to be on. Then what you do is you're going to be like, okay, so like I said, I want you to, okay, it's going to be under site. It's going to be under student lectures. You're going to want to make a subdirectory for your topic. New directory. Novelty search. Then, because I'm really lazy, my recommendation is, the description might not be a good one, but if we go to like the topics, I don't know, just copy one of the existing RST files, paste it into here. What do we want? Novelty search. And just holy hell, this is slow. Novelty search, update it with what I want. Maybe change some of these things around. And as you're going, I don't recommend you make all the changes and do one big commit. No. You do a few changes and then you'd be like, okay, copy RST file. And then I would say commit. Right? Commit. Okay, great. And then I'm going to come along and be like, okay, well, what is it? Right? Maybe I want a section called what is it, right? And like, okay, I'm going to want to want to get rid of all this stuff because this is obviously not relevant for novelty search. Right? And then maybe after I've made a couple more changes, I go and be like, okay, motivate topic. I commit a little bit more. Right? These are just showing the fact that I deleted all that extra stuff. And if I scroll down, it'll show you in green what I added. What is it, right? So committing the changes, and then, okay, how to do it, right? You make the changes. Maybe you want a figure, so you go and maybe you find a figure, you put it in your subdirectory, and then you can, the name of my figure. Make sure they're PNGs. They don't have to be, but I'm going to make you make them PNGs. Right, and then I go here, okay, maybe after a couple more changes, you're like, I added a figure, right? And then once you're all done, what is happening? Once you're done, you say publish branch. Once you're done, now you don't actually have to do your whole topic in one pull request. You can make half of your topic and be like, I'm going to make the other half after. I just want to get this part done, get it out of the way, and then I'll make a new pull request to fill in the second half of the topic or something. That's fine. But whenever you're happy with some amount of work that you want to just like get done and have me look at and approve before you carry on if you'd like. Now, you can do the whole topic at once and then submit the pull request and I'll read it then. But whenever you want to make a pull request, you just, in this you say publish branch. So this then pushes it to the repo. I'm expecting it to be insanely slow. It shouldn't be. And then when you're done, yeah, we can create pull request. And then it's actually going to take you right to the website on where you do that. You add in your little, if you read the contribution guidelines, which you should, it says like add little like emojis. So this would be, the relevant one is that. Right? There's no related PRs. That's just topping at the topic of, what is it? I started doing I just wanted to get something down. Why? Where, how, not really needed. Testing. Testing, what you would say here is if you built it locally, and the instructions on the README would be how you build it locally. If you go to the GitHub repos README, it's hilariously simple. If you created the virtual environment, which you would need to do to use it properly, here's how you build it locally. Sphinx-build space-b HTML, you're building it as HTML. And then you have like your source directory and your output directory. This, you just say like, if I was doing it, it would be like, if I look at my folder, it's like under, the source directory is site, and my target directory that I have locally is called like build. So I would just type that in, hit enter. It would take whatever's in the source directory and build it as a website and store it in the output directory. Just try it out, you'll figure it out. It's pretty simple. Oops. Testing, I built local, looks good. Additional notes, if there's anything else you want to say, I know I'm not done yet. It's only part done. I don't know, whatever you want. You won't be able to add labels, I don't think. I would have to be the one to add labels, so you leave that alone. When you're done, you hit create pull request. Now I'm not going to do that because this one's entirely nonsense, but you create it. As soon as it's created, actually no, I'll create it. So let's say you created it. Suddenly, I would see, oh look, there's a pull request. Cool. I'm gonna go look at it. right? And I can actually look at what you've changed, which is kind of cool, right? And even now, if it's the first time you're submitting a pull request, I have to approve these actions. But these actions, one of them is actually to build like a local version of the site that I can download and look at the build version to make sure it looks good too. And then once I'm happy, maybe I give you some comments. This is terrible. Try again. I don't know. I'm not going to be that mean. So you do that. And then maybe you get it. You make some changes. You update your pull request. So you go here and you're like, oh, yeah. Ignore this PR. That's because of my buddies looking at it. Because I've got some friends that'll look at my, that. Anyways, so they know it's garbage. So, like maybe the feedback was, you forgot a period, go add a period. And yes, I'm going to be that obnoxious. If it's going to be on the website, it's got to be good. So, oh, okay. So I added the period. Let me save. Go here. Added dot. Commit. There. We can see the difference. It's even showing you. My God, it's slow. And then, okay, once I've updated, I can push it back to origin. That's push it back to the website. If I go back to the website, you'll even see, oh, look, a new commit. So I can actually go look at, well, what does it look like now? And if I go back here, I can see, yeah, there's the period. It's kind of neat too. I can even go click this particular one. It'll show me the specific changes on that commit. That's why it's good to have commits frequently, so it's easy to see what was done. So, oh, this is what was changed in that one commit. And then once I'm happy with it, I will go, I will approve. Now, I can't approve it because the checks aren't done. I'm guessing that's it. But I'll approve it. And then once it's done, I will squash and merge, which means it becomes part of the actual website. Okay. So I'm just going to get rid of this pull request because it's obviously nonsense, right? Cool. There. So there's a quick little crash course on how to get started. This is not exhaustive. Yeah.
So realistically, I'm probably going to be doing it during the reading week, and when you're going to be available by email during the reading week, then I'm probably.
I'll be available-ish during reading week. I'm not going anywhere, right? So I'm working during the week during reading week. I'll be in for office hours too if you want to come swing by. I get lonely. Please come see me. But yeah, cool. Other questions? If you're stuck on something with GitHub, and I'm not saying this to say don't email me, and I'm not saying this to say don't come to office hours. No, please do. But honestly, I'm not a GitHub expert. I'm not a Git expert. So some of the questions you ask, I might need to look up. So you could just cut me out as the middleman and just look it up. If you go and watch another 4-minute long GitHub tutorial, you will probably learn everything you need to know. That's how I learned. I found there's probably literally billions of hours of GitHub tutorials on YouTube currently, right? So you can, if there's anything you don't understand, just go look it up. I'll try to help you if you need help, but it's probably easier to Google it than it is to come see me in office hours, right? Just saying. Other questions at all? Anything? All right, cool.
So the topics, the things for Richard to say, right?
Yeah, email me. Now, I'm going to recommend because I haven't checked my email since the end of work yesterday, so I don't know how many have come in since then. And if you go to the website, where's the website? And you go down to the student lecture, you'll see some of them are already actually taken, right? So I've only gotten 3 people's confirmed so far, and I've removed some of the dates. If a topic you want, if let's say you email me right now saying, I want to do Artificial immune systems. You already emailed. Okay, cool. But let's say you just email me right now saying, I want to do artificial immune systems. And I go check my email, but they emailed me an hour and a half ago saying they want to do artificial immune systems. I'm going to email you back and being like, try again. So to hedge, what you can do is you can like send me a list of things. You could be like, well, first I want to do this, and if that's not available, I want to do that, right? And then I can go like, okay, perfect, great. It makes things easier. Cool? This right now is the most this is up to date as of like 4 p.m. yesterday. So I may have gotten a dozen emails since then. I don't know. So no guarantees there. And if you don't tell me a date, I'm going to give you the date I want to give you. So deal with it. I don't think the time crunch is really going to kill you. I think you've got plenty of time. If it does kill you, that's on you. You started too late, right? You'll be fine. Any other questions? You'll have fun with it. The student lectures are always, I really enjoy them. I think the students really enjoy them. I think students get worried about them, but I think once they do them, they realize, oh no, that was awesome. Like, I think people end up having fun with it. Like I say in the description, it was funny. Marking details. The key to making a good lecture is just don't make it boring. First and foremost, obviously you want to make it informative. Don't make it boring. Boring student lectures are terrible. Boring lectures are terrible. When I did this, my buddy, he was like, well, you better reference good examples of non-boring lectures then. Meaning that like mine are boring. And I was like, oh, he got me. But anyways, look at this, last updated yesterday. See, I swear it was updated yesterday. Don't make it boring. Have fun. If it's boring, it's probably because you didn't have fun. And if you're not having fun, you're doing it wrong. Make it interesting. If you want to write code and include code, you can, like, by all means, I'm happy to have your code on the web, like to store on the repo too. Very happy. And the good news is everything that's saved on the repo, if it's your pull request, for time immemorial, it will always be labeled as you. This was your code, you submitted, it's all you, so you get full credit for it, which is cool. But if you do write your code, you're going to want to submit it to the source folder. If we go to the GitHub repo, it would be under source, because that's, where the source code goes. And if you submit code, if necessary, I'm not going to accept anyone's code unless they write unit tests for them. So be warned. I'll be happy to see code, but if you don't write unit tests, no good. And if you're worried about how you write the unit test for them, just look at the example unit tests I wrote and you'll be a whiz. Right, here's a couple unit tests for crossover, right? They might look scary. They're actually like 99% boilerplate. That's it, right? Raise your hand if you've never written unit tests before. All right. The good news is they're actually really easy, but when you say you do it, it sounds like you know what you're doing. So easy peasy. Just look at an example of one I've already done if you want to go that route. Adding code is not necessary, but obviously it could be valuable. But yeah, have fun with it. Don't make it boring. Lectures that always try to follow a framework are 9 times out of 10 boring. Right? Lectures that try to be like, okay, today I'm going to talk about novelty search. And novelty search is blah, 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 blah. And then first I'm going to explain what it is, and then I'm already bored. No. Have fun. Make it interesting. Make it engaging. People will care. I'll like it. You'll get more points. And it's all about the points, right? So there we go. Other questions about it? All right. Okay. So that was the marking details. Back to experimenting, with n queens. Okay. Okay, you know what? Yeah, before anything, here's what I want you to do. If you have the GitHub repo already forked and download on your computer, you already have access to no, not there, not here. Where's source? There's source. GAN queens. So here is the N Queen's genetic algorithm, and I think at the bottom, oh, I didn't even include the plots. But if you go to the GA max bit string, I think you can basically take that. And paste it. All right. Oops. Tab. Have to import plot. Anyways, you get the idea. Take a few minutes, run this GA a couple of times, maybe tinker with some of the parameters, but run it multiple times with the same parameters and generate the plots, and then we'll go from there, we'll talk from there. So take a few minutes and do that. I guess I'll pause the recording because it'll get really boring. Continue. All right, we're back. Okay, so, yeah, all right, the N Queens. So if you're running it, so here's an example, what did I run it as? With N of 20, here's an example of a learning curve, right? Who here saw a learning curve that looked kind of like that? What?
I didn't get the plot.
You didn't get the plot, well, or whatever, fine. If you did, you'd probably get a learning curve that looks something like that, all right? But of course, I'm saying something like that. Because how much randomness is involved in these algorithms? You randomly initialize the population. Selection is random. Look, when I say random, maybe it's stochastic. There's randomness involved, but you've got a higher probability to pick better ones, but it's still random. There's the randomness there. Whether or not you do crossover or mutation is random. And then there's randomness in how that crossover or mutation is done. There is a lot of randomness going on. So when I hit run, if I hit run and saw the exact same plot twice, I should have just bought a lottery ticket instead, because the odds of that are insane. So every time I hit run, I'm going to get slightly different results. And the variability between runs might be insane. One run I might get terrible results, the next run I get okay results, then terrible, then even worse, and then really good, and then okay, and then terrible, then okay, then really good. It could be all over the place. So if you think to yourself, all right, I'm going to run the algorithm once, make a couple of changes, run the algorithm again, and ooh, I got better results. So therefore, these settings are better. You're fooling yourself. Because the randomness, right? Like, I could run the same algorithm with the exact same hyperparameters and get wildly different results every run. So how could I make a comparison between different sets by doing one run? Does that make sense? How it would be problematic to do a comparison like that. You can't. If you do, you're committing a sin. It's bad. So, yeah, okay. These algorithms are stochastic. You're going to have variability between each run. Every time you run it, you're going to get different results. There's the initial population, selection operators, and everything. Everything's stochastic there. So it's not possible. So it's possible, but everyone will laugh at you because your conclusions will be terrible. It's not realistic to run two versions of the algorithm once, and like each once, and then be like, well, that one gave me better results, therefore it's better. That's foolish. You can't do that. So a learning curve like this is really good for a quick and dirty look at, well, how did those settings do? Right? I would look at this and be like, it looks like it's converged, but maybe I'll try running it for 500 generations just to see. Right? So a learning curve is really good for tuning your algorithm, but as soon as it comes to like really making big comparisons, looking at single learning curves or just final results of one run, it's no good. So instead what we do is we create a distribution of results. So here's an example of what you do. I'm going to run the algorithm with the same settings. So I have a hypothesis. I think that if I make the algorithm run like this, it's going to be better than like that. I'm going to run this one 100 times and save all the results. Then I'm going to run this one that I think is better, and I'm going to run it 100 times, and I'm going to save the results. Then I'm going to do some summary statistics on these 100 runs results. Summary statistics are things like, look, we've got a, do I have a picture of it? Here's an example of a distribution. There. On this problem, this is the fitness, minimization is the goal. So it looks like we've got 0 to 1, 1 to 2, 2 to 3, 3 to 4, right? So I did 100 runs here, it looks like. 50 of them finished with the best fitness being 1, meaning there was 1 conflict. It looked like maybe 15 of them, when I look here, maybe 15 of them actually got like the optimal. And then what do we got, like 30 something or other had 2, and then a few, maybe what's that, like, I don't know, 3 or 4 had 3 conflicts. All right, so this is the distribution of running an algorithm once. Now the distributions are going to look wildly different depending on the problem we're solving. Did anyone generate a distribution of results for the TSP? You did? So I'm guessing your distribution looked wildly different than this, right? Because it wasn't a problem where we were looking to get 0, right? You were just, the fitness could have been in the millions, right? But that is an example of a distribution. I can generate some summary statistics of this distribution. But really, what I want to do, if I've got this algorithm and I've got that algorithm, I want to compare them. The ultimate goal is to actually compare the distributions. Now that's not easy to do at this stage. That's where like the heavy-duty statistics come in. Heavy-duty. That's when the less than trivial statistics come in. But the trivial statistics, things of like, well, what's the mean of that distribution? What's the standard deviation? I can generate some summary statistics of this distribution, and I can compare the summary statistics. So maybe after 100 runs, that algorithm was, on average, doing worse than that algorithm. The average of the results, the average of the distribution of the 100 runs was better for that one than that one. So suddenly, this is a much better way to compare your algorithms. I'm not just running it once and saying, there, that's my result. I'm running it another time over there. That's my result. Compare those. No, we know that's no good. You can't. The randomness is crazy. So run it a bunch of times, get a sense of how it performs, and then do that comparison. That said, this is only an improvement on comparing one run on another run. This isn't the most correct way to compare the algorithm's results, but it's a hell of a lot better than just comparing one run to one run. Comparing one run to another run, terrible idea. So what was I saying here? One, calculate. I was saying do this, but for the sake of time, we won't do that right now. If you make the problem harder, yeah. If you make the problem harder, shoot. You know what, I think tomorrow, or when's the next time we have lecture? Friday? Friday. On Friday, try to have, on Friday, what I'll do is I'll go through this topic, because there's stuff in here that's worth talking about, but some of this is like activity time. On Friday, we'll try to do the activity again. Maybe everyone's kind of got everything running. And if not, like I can do it and I can show you what I mean. At the very least, I'll still do that on Friday just to kind of give you a sense of what I'm actually doing and why it's important. All right, change representation, comparing results. Okay. This is what I'll finish with today. So the summary statistics of distributions is a good way, again, for a quick perspective of comparing the results of the algorithms. I can have 5 different sets of parameters and settings I have for my algorithm, but I would want to generate 100 runs, or some sufficiently large number of runs. Usually the rule in computer science is 30. That's the magic number. But it's a bullshit number someone pulled out of their ass. I like 100. I think it's better. But, if I have to run an algorithm 100 times versus 30, if time isn't an issue, fine, use 100 runs. If time is an issue, well, maybe 100 runs is a problem, especially if you're looking at the place where a single run takes a few days, Anyways, comparing the summary statistics of distributions is a great way for a quick and dirty comparison, but it's really not a safe way to actually compare, because it's possible to have distributions that have similar means but are very different, and those with very different means but are actually not that different distributions. I know it sounds weird, but I think us as humans, we like to compare single data points, and it's not easy to compare a distribution. So for example, what do I have here? Okay, if the result when using crossover X has a better mean than the result using crossover Y, then X is better, right? Well, for example, from the data points in the below figure, the mean genetic algorithm with a crossover rate of 70% was 2.1, and the mean of a genetic algorithm with a crossover rate of 20% was 0.55. It would seem that the crossover rate of 20% gives better results. That summary statistic makes it pretty damn clear that it is, right? But is it? This is a poor way to perform a comparison. It doesn't mean that your conclusion's wrong. It means that the way you made the conclusion wasn't the best way. You might be right, but because the way you're making the conclusion isn't the best way, it may lead you to make poor conclusions. It doesn't mean the conclusion is wrong, but it means that our ability to be confident in our conclusion just isn't there. This is because the goal is actually to compare the distribution of results themselves, not the summary statistics. We want to compare the algorithms, and the algorithm's output is their results, the distributions. The summary statistic is just a summary of that distribution. It's not the distribution. We actually want to compare the distributions. So here I'm plotting two distributions against each other. Look, I look at that. First, I'm going to do an eyeball test, like visually comparing the distributions. I look at this, and suddenly I'm thinking, yeah, the mean was better. And look, clearly the one distribution, the algorithm that has the orange distribution looks like it's probably doing better than the one with the blue. I mean, both are capable of getting the optimal solution, but the orange one seems more likely to get us the better one, I guess, right? What I'm saying here shouldn't be mind-blowing. This should be fairly intuitive. So, raise your hand if you ever heard of p-value before. Yeah. Raise your hand if you know exactly what that means. Yeah, see, here's the problem. You do. Awesome. One person. Good job. P-value means probability value. So here's my issue. A lot of people, when they learn this stuff, they are not ever shown where the hell that came from and what it means. And I'm going to show you this later in the semester. But the p-value, what it's going to tell us is, it tells us the probability that two distributions, I'm going to be loosey-goosey with my terminology here just for the sake of being high level and communicating the intuition. I could be a lot more precise. I'm not going to be. But really, it's telling you the probability that the two distributions are the same. If I have a p-value that's really high, like a p-value of like 0.8, that tells me there's like an 80% chance that those distributions, although they might look a little different, but if I'm using some statistical test that gives me a p-value and the p-value is like 0.8, there's an 80% chance that those distributions are actually basically the same. If I kept running for more than 100, maybe 1,000. If I keep running, it's going to become more and more obvious that the distributions really aren't that different. If a p-value is very low, we say, okay, then maybe the p-value is like 0.001. Well, there's a 0.1% chance that we've got a p-value there's a 0.1% chance that these distributions really are the same. And if with a low p-value, that means that the distributions are actually probably different, which means that this is where you hear that phrase, significantly different. So they're different, and there's a meaningful difference. And then, of course, we've all heard of that magic alpha value, 0.05, right? If it's less than 0.05, if it's less than 5%, you have a significant difference. The sad news about that is that's a bullshit number pulled out of thin air that people have used for no real reason. Because it actually means that there's a 1 in 20 chance that the difference that you found is actually bullshit. But we'll pick up here Friday.